Everybody have a wonderful weekend where the time changed? It's always nice in the fall because you get an extra hour. And I know what you did with your extra hour. Homework, right? That's what I did with mine too. Now we're past tornado season. I'll shut the window. So last time we did an introduction to statistical hypothesis testing and got all the terminology and all that kind of stuff. But today we will start to formally apply this process to some example problems. But a little bit of review before we do that. What is a null hypothesis? What does that mean?
Not.
Okay, not or none. So think about an example. Remember the example we did was a proportions example where you guys guessed the number, or you guessed whether I had flipped heads or tails, right? And then we counted the number of successes you got out of the 10 times, right? So the null hypothesis means no what?
ESP.
No ESP, right? So sometimes you have to figure out, well, if the null is true, that means none of whatever it is. You have to figure out, well, what is that in terms of symbols, right? So that's assuming, well, if you have no ESP, then the proportion of correct guesses would be equal to some number. You have to figure out what that number is, okay? So what is a p-value? And by the way, this is the one time in the whole semester when I will tell you verbatim one of the questions that will be on your next exam. Everybody goes, ooh, where's my pencil? What is a p-value?
Probability
It is a probability.
of observing.
Probability of observing
Data.
Like our study, or even further than
Okay.
the null.
The probability of observing data like we got, or data even further from the null hypothesis, if the null is true. And that's an important if. Now remember, an if statement like that means that p-value, that probability value, is a conditional probability. We condition on the null being true, then we compute the probability of getting data like we just observed. And if that probability is really small, then what do we say about the null hypothesis? Reject it. The null is probably not true. If that probability is fairly big, then we say, well, the data like this is reasonably likely to happen when the null is true, so we have no evidence against the null. Right? Well, last time we had down like 5 steps that incorporated the scientific method. And I started the process of rewriting them as 5 steps to do hypothesis testing. So today I'll finish that. And then real quickly, we'll go to one of the homework problems at the back of the section and work it through as an example. Excuse me. So, step number 1. Check the assumptions necessary for valid inference. And I started to write valid hypothesis test, but this works for confidence intervals too. The assumptions are the same. So we went through these assumptions when we did confidence intervals. Check the assumptions. Now, we're going to do, in this section, we're doing significance tests for proportions. So what are those assumptions? What's the first assumption? Always.
If it's normal,
Nope, that's the second assumption. First one, before that,
comes from a random sample.
data must come from a random sample. Data come from a random sample. So that's the first assumption. Now, unfortunately, with limited board space, I'm trying to write big enough so that the video can pick it up. I'll end up having to erase these steps, and then so they'll be in your notes, and I'll just refer back to, okay, now step 1, we're going to do this, or whatever. So step 2 then is what? I'm not step 2. Assumption 2, second assumption. This is for proportions.
If the spread is normal.
That's for means. But it is related to that. She said you said the spread is normal. I'll paraphrase, the sampling distribution is normal. And that's right, but for proportions, we had a sample size requirement. We had to have a big enough sample that the central limit theorem tells us we've got a normal distribution for p hat. And what is that sample size requirement? Okay, that's for means. She said it has to be at least 30. If it was a means problem, then that's it. But this is a proportions problem, so it's sort of like that, but
At least 15 successes.
at least 15 successes and 15 failures, which those two add up to 30. But remember, we did an example, well, but if your p is like a really small p or a really big p, then you have to get more than 30 in order to get 15 successes. So at least 15 successes and 15 failures. If that's met, then our p hat will follow an approximate normal distribution, and we'll get valid inference when we use z critical values for our confidence intervals or our test statistics when we do hypothesis tests. Okay? Now, in order to get credit, get the points that this is worth on the exam, don't do this. Step number 1, check. I get that, just a check mark. Or sometimes they'll write it out. Yeah, assumptions are met. What I want is I want you to prove to me you know what the assumptions are and that you did actually read the problem, check and see that, yeah, they're met. So I want you to write them out. Say, the problem says the data comes from a random sample. It'll say a random sample of 1,400 students was taken and blah, blah, blah. If that tells you, okay, it was a random sample, so that assumption's met. Right? And then you say, and it says there were this many successes, which leaves this many failures. Sometimes you have to compute that one. Therefore, we do have at least 15 of this and 15 of that. Don't just say, yes, assumptions are met. Right? I'll say, true, -3. Okay? Step number 2. Step number 2 is the same as it was in the scientific method, only it's moved down a step. It's state your hypotheses, right? So I'm going to, instead of the word state, I'm going to say write hypotheses, both null and alternative, using proper notation. So if I'm doing a hypothesis test about a proportion, what should my null hypothesis look like?
Equal.
And it has to have an equal sign in it, that's right. What symbols do I use?
H-O-P equal to.
A p equal to some number, right? In general, we write that number as p sub 0. But that's just a placeholder for a number like 0.5 or 0.25 or some number will go there. Right? When we go to 2 sample problems in chapter we in now? When we go to chapter 10, we'll do 2 sample problems. This will look a little bit different. But for 1 sample problems or proportions, it'll always look like this. Your null will always be p equal some number. And that number you get out of the reading. Okay? Don't write this. What's wrong with using a p hat instead of a p? P hat is the sample proportion. We don't have to do a hypothesis test about that. We know that number. We just We compute our sample, we get our sample, we compute what our p-hat is. I don't have to do any fancy schmancy statistical inference to know something about p-hat. I just compute it and there it is. But I don't know is p, so I have to make hypotheses about what that real p is. So don't put mu, because that's what it would be if it was a means problem. Don't put x bar, it's a p. So proper notation, it needs to be this to get full credit. Okay. What about the alternative?
Has to have something that's not an equal sign.
It has to have something that is not an equal sign. And you were very careful the way you worded that, not to say it needs a not equal sign, right? Because that's one of the three choices it could be. What are the three choices?
Less than, greater than, not equal
A
to.
less than, a greater than, or a not equal. It would be one of those three, right? And it can only be one of those three. These two, the less than or the greater than symbol, what are those tests? One-tailed or two-tailed?
One, no.
Those are one-tailed tests, right? The not equal is a two-tailed test because you're going to reject the null if you get out into either one of the tails. Far enough out into either one of the tails tells me, well, it isn't P. Okay? Okay? So, now, on these steps, step number 3, I change it a little bit from what the book says, but when you do the online homework, it's going to expect you to answer it the way the book says. So in the book says, compute test statistic and p-value. No, I'm sorry. It says compute test statistic. And then step 4, it says compute p-value. And I changed this a little bit because when we do it, we're going to do it on our TI-83s, and it's going to do both of those at the same time. It's just going to give us, here's the test statistic, here's the p-value. Okay. So instead, what I do is I move this one down to there, down to step 4. And at step 3, so in class, what I want you to use is step 3, determine the correct procedure. So what I mean by procedure is on your TI-83, where do I go? I push stat, and then I go to test, and which one do I go down to? When we did confidence intervals for proportions, which one did we use? Remember? We went stat, then test, and then down to what?
INT.
Yeah, it had an INT, but it had some other stuff in front of that. Remember? It's okay, I can wait. If you don't remember, take your calculator, hit the stat button, go to test, and go down and go, oh yeah, I remember what he's talking about. And which one was it? To do a confidence interval for a proportion.
Oh, the
One prop Z. Good. So now we're not doing confidence intervals, we're doing a hypothesis test. But guess which one it is? It's the same scenario, one sample proportions. But now it's a test, not an interval. You ought to be able to look at your calculator and figure out which one is the correct one to use. One prop Z test. Okay? So what I do is I say step 3, do that. And then step 4, compute the test statistic and the p-value, all as part of that step. And so basically it's step 3, determine which procedure you should be using. Step 4, now use it. And then when you do it, it will give you the p-value and the test statistic. Okay? Now I'm going to come back to this test statistic because I haven't defined that for you yet. That's the first you've heard of it. But I'm going to say what step 5 is and then I'll come back to that. So step 5 is make conclusions in the context of the problem. So what do I mean by the context of the problem? Well, here's what I don't want. Step 5, conclusion, reject the null hypothesis. And then go on to the next problem. That may be very true, that is what you're going to do, but I want you to tell me in words, in English, that my mother could understand of what your conclusion is from that study you just did. So if you're doing a study about ESP, and your null hypothesis is that you don't have ESP, then I want your conclusion to be, I'm going to fail to reject that hypothesis, therefore there is not sufficient evidence to say that this person has ESP. Write it out in a sentence that is in the context of the problem. Right? If I'm doing a study about the proportion of allergy sufferers who get relief when they take drug A versus placebo, then my null hypothesis would be that drug A portion is the same as it is for placebo. So when you make your conclusion, you say, I have sufficient evidence to reject the null hypothesis, meaning that the proportion of allergy sufferers who get relief is greater on drug A than it is in placebo. So you better hear something about what's being compared and the population of interest, and those not just reject the null or don't reject the null. Okay? So that's step number 5, make conclusions. Now, how do we make conclusions once we know the test statistic and the p-value? Remember that thing we called the alpha level, the significance level? How did that relate to the p-value?
It's a small p-value, it's less than or equal to the alpha.
Exactly. Okay? We say a small p-value is evidence against the null. Reject the null if you get small p-value. And that alpha level, the significance level, is the cutoff for how small is small. So if it gets below alpha, then you're going to reject the null. If it's not below alpha, then you fail to reject the null. Now I haven't talked about this yet, but I'll start harping on this. Don't ever say, I accept the null as being true. All you can do is, I reject the null or I fail to reject the null. So in other words, there is either enough evidence to say the null is false or there's not enough evidence. You never have enough evidence to say the null is true. Don't ever write it down. Okay? Does everybody understand the 5 steps? Okay? Now let's work a problem. And I'm struggling a little bit. The problem, I'm going to use a couple of different problems to do, but I want to start with one that
Are you going to define test statistic?
oh yes, I am. I was just having that same thought because I read this, and the test statistic is Z, and I thought, oh, I haven't told them what that is yet. So let me do that, and then we'll work a problem. So test statistic remember that the sampling distribution of p hat is approximately normal. So it looks like this. Where will it be centered?
P-value?
Not p-value,
P?
at p. It'll be centered at p, which is the true population proportion. Now, do we know what p is? No, because if we did, we wouldn't be taking samples and trying to estimate it, right? But when we have a null hypothesis, we're saying that p is equal to p0, right? So if we assume the null is true, then we do know what p is. So like on our example with the guessing the coin flips, under the null hypothesis of no ESP, we expect you to guess 50% of them correct. So we'd have p equal 0.5. So if the null is true, then this p is p sub 0. Right? So I'll put in parentheses, assuming the null is true. So if the null is true, then we know the sampling distribution of p hat. Right? The test statistic gives the number of standard errors p hat is from the null. The null is p0. That's the test statistic. Now, what is it that we've computed along the way this semester that tells us number of standard errors? No, not standard deviation, but a z-score. And it's number of standard deviations, and then when we went to sampling distribution, we started saying standard error instead of standard deviation, but it's the same idea. And that's what this is. We're going to call it z. Z equals, now do you remember how to compute a z-score? You take the value and you have I mentioned that the final is cumulative? So stuff that you learned in chapter 1, you still need to know. So how do you compute a z-score? No, that's a standard error. And I'm going to ask you that in a second too. But the z-score is you take the value, you subtract the mean of those values, and you divide by the standard error. Right? And so that's what this is. It's p hat, the number of standard errors that p hat is from the null. Well, the null is p0, and that's the mean of the p hats if the null is true. So that's the center of the distribution of p hat when the null is true. Now, if I want to convert that to number of standard errors, I need to divide by the standard error. So what is the standard error of p, or of p hat? Chelsea, you started to give me that.
Square root of p hat times 1 minus p hat over n.
Over n. Okay? Now, that's the standard error we use if we do a confidence interval, because we don't know p. But do we know p now? We do, because we're assuming the null is true. So what is p? If the null is true, p is p0. So I don't have to use p hat, I can put in p0. So that's the test statistic for testing whether p is equal to p0. Okay? Now let's suppose that we did a bigger study on your ESP, and we found that that somebody guessed p hat correct 60% of the time, 0.6. And we'll say we flipped it 50 times. So n was 50. Right? What would that test statistic be? Well, what would p0 be? If I'm flipping a coin and you're supposed to predict what the flip was. 0.5. So this p0 would be 0.5. So I would have 0.6 minus 0.5 divided by the standard error. And that standard error would be 0.5 times 1 minus 0.5, because I'm using the hypothesized value, not p hat, but p0, divided by n equal 50. So give me that as a decimal. What did you say? 0.005? That's the standard error, right? That's the bottom? No, that wouldn't be the bottom either.
I didn't do the square root of it.
Ah. 0.0707, like that. Is that what everybody else is getting? What is the standard error on the bottom, by the way? I want that number too, because I want to draw it on my picture. Somebody do just the bottom of this. That number?
Yeah, that's what that is.
So that's just about, okay, well, that's good. Then I'll just do that.
The answer for the overall
And-
is 1.414.
In the top, I can do the top in my head. 0.6 minus 0.5 is 0.1. So then, dividing those, you get what? 1.4, what?
142.
142, like that?
Mhm.
Okay? So, if this is 0.5, the null hypothesis, where is 0.6? Is it about there? Or is it about there? Or is it about there? Or is it out in the hallway? How far away from the null is it? Well, it's 1.4 standard errors from the null, and this dotted line halfway down the hill is how many? That's one standard error, so I need to go, okay, there's two standard errors, I need to go 1.4, so it's about right there, right? So that would be 0.6. That distance is 1.4 standard errors. Now, what's the p-value? Well, the p-value depends on whether it's one-tailed or two-tailed. So let's say it's a one-tailed test. You have to do better than half in order for me to think you have ESP. Where would the p-value be? How would I compute the p-value? Okay, now what is the p-value again? I keep forgetting that.
Probability of
Probability of observing, I don't know.
Data like
Data like we observed, or further from the null, if the null is true. So the if the null is true part, it says, okay, this is your picture. If the null is true, then this distribution is centered at 0.5. So where do I shade for the p-value? The probability of getting 0.6 or further from the null. That way, right? So this is my p-value. That shaded region is the p-value. Now I could compute that using normal CDF on my calculator. I'd say normal CDF from 0.6 to infinity with a mean of 0.5 and a standard error of this thing, 0.07, and I'll get the p-value. Go ahead and do that for me real quick, because now we're going to do it using one prop zn, and hopefully we get the same answer. So this thing, let me draw an arrow there. This is normal CDF at, I guess I can get rid of this for now, 0.6 up to infinity. I don't need very many nines since I'm in decimals here. And a mean of 0.5, the null hypothesis, and a standard error of 0.0707. 0.0786. That looks too small.
So I got.
That's what you're getting? Okay. The reason I think it looks too small, and it must not be, but is if I was at 2 standard errors here, how much area would be out there? 0.025, right? Remember empirical rule? And so I thought being a 1.4, I'm more than halfway back this way. I thought it would go up to more than that. But apparently not. Yeah.
So 0.0707, that is the standard error, and 1.4142 is the test statistic.
That's the test statistic. So this is Z test statistic. Okay? This is the p-value. Okay? Now, get your calculators. Oh, that's the wrong button.
How do you do the p-value again on your normal CDF? Okay.
Right there. Now we're going to do it using the TI-83. So up here on the top, I'm going to clear that out. And we said to get both the test statistic and the p-value, we need to go to 1 prop z test. So do that. Push the stat button. Then go over to test. And then go down to 1 prop z test, which happens to be the 5th one down, so you could just hit the number 5. Now the first thing that it's asking is P0. And what is P0 for this problem? 0.5. In fact, let me just put that in here. That means the number that's in the null hypothesis, the sub-zero hypothesis. So P sub 0 is 0.5. What's X? No, it's not 0.6. P hat is 0.6, but X, your calculator wants X, number of successes, not proportion of successes. So we had 50 trials, so it'd be 60 out of 100, so how many out of 50? 30, right? 30 out of 50 is 0.6. But how you get that if you don't do it in your head, it's X equals N P hat, right? So P hat was 0.6, N was 50, so that's equal to 30. So enter 30 for X, and then N is 50. Now this line that's blinking right now says prop, then it has a not equal P0, a less than P0, or a greater than P0. And it's asking which of those is your alternative hypothesis. So we want that the proportion is greater than P0. So pick that far right one. Mine's already highlighted. So then you go down and hit calculate. If you hit draw, it'll draw this picture. And it'll shade where the p-value is. And that's useful to do sometimes.
Does it tell you the p-value?
What?
Does it tell you the p-value?
Yeah. So there's the results. It says, first line it says what we tested. We tested the prop greater than 0.5. Always look at that and make sure it matches what you think it should be. If you enter P0 incorrectly, then you should notice that, wait a minute, that top line doesn't match what I wrote down for my alternative hypothesis. It should look like your alternative hypothesis. Second line says Z equal 1.4142. There it is. Okay? P-value is the next one. There's two P's there. One has a blob on top of it. And that blob is the resolution is bad, but it's a hat. So that's P hat. So P hat, we said was 0.6, and that's what it says, so that's good. That's just a check to make sure we got things entered. And then p-value 0.0786. So you can see that the p-value is just simply being computed as an area under the normal distribution. Okay? Any questions on that? So what would the conclusion be from this test? That's step number 5. This test statistic of 1.4 and a p-value of 0.0786, that's step 4. Once you have those two things, really all you really have to have is the p-value. You can make your conclusion. So what would the conclusion be? Would I reject the null and say, ooh, this guy's got ESP? Or would I say, well, the evidence is not strong enough to say they have ESP? You say not strong enough?
Yeah.
How come?
I don't know, I'm just guessing.
Well, you guessed right.
I just guessed because 0.6 does not seem good enough.
Oh, so you just went back and looked at the data and you did the eyeball test.
Yeah.
But I want you to use the p-value, right? What is the p-value again? I keep forgetting that.
Probability of
further from where that is if the null is true.
It's the probability of getting data like we got, or further from the null, if the null is true. So it's saying you can get data like 0.6 or even bigger than 0.6 7 or 8% of the time. And when do you reject the null? If the p-value gets small. Is that small? Is it small enough?
No.
What do you use as your cutoff for small enough?
0.05.
Your alpha level. And what's our alpha level? Trick question. We never said what our alpha level was. When in doubt, your alpha is 0.05. So this one is bigger than 0.05, so we would fail to reject the null. But I would always say, as a statistician, we fail to reject the null, but barely. It's close, right? You would want to say that, you know, I don't have strong enough evidence, but I almost do. Right? Now, I made this up. I didn't actually flip a coin 60 times and have anybody guess, and getting 60% correct would be, 60% of 50 tries. That'd be pretty good for just random guessing. But okay, now let's work the problem. We're going to do 914 on page 426. And we're going to do it all the way through. We will eventually hit all of the 5 assumptions, but the way that the problem is worded, they don't have us do all 5 in order. But I'm going to do them kind of as we come to them here in this problem. But let me first read the problem. It's kind of an interesting scenario. This is an actual study that was done. Dogs and cancer. A recent study considered if dogs could be trained to detect whether a person has lung cancer or breast cancer by smelling the subject's breath. The researchers trained 5 ordinary household dogs to distinguish by scent alone exhaled breath samples of 55 lung and 31 breast cancer patients from those of 83 healthy controls. Now that's an awkward sentence in my opinion, but what they're saying is we've got 83 subjects and then we have controls to match those, right? So the study design is a little clearer after the next couple of sentences. A dog gave a correct indication of a cancer sample by sitting in front of that sample when it was randomly placed among 4 control samples. So what they're saying is they take somebody that they know has cancer, they have them breathe into a device that captures their breath, and then they put that on the floor along with 4 non-cancer ones, and they mix them up in a random order, and the dog has to pick out which one is the right one, which one has cancer. Okay? See how they're doing this? It says the researchers blinded both dog handlers and experimental observers to the identity of the breath samples. Right? So that's just quality of the design. You wouldn't want the person that's leading the dog around to know which one is the cancer sample, because they could bias it, right? Probably unintentionally, but they could bias it. Let P denote the probability a dog correctly detects a cancer sample placed among 5 samples when the other 4 are controls. So P is the true population proportion of the time the dog gets it right. Okay? Set up the null hypothesis that the dog's predictions correspond to random guessing. Set up the null hypothesis. So this is step number 2. Set up the hypotheses. And right now they're just saying, what is the null hypothesis? It says, set up the null hypothesis, and remember, null means none. It means the dog cannot tell, has no ability. Right? So if the dog has no ability, what percent of the time would you expect him to guess the right one? Not 1 out of 4, but they have 4 controls and 1 cancer. So there's 5 of them down there. So they got 1 out of 5. Right? So if the null is true, the dog is just guessing, so the proportion of the time they get it right, call it P, should be equal to 1 in 5. So 1/5. Now you can leave it as a fraction, that's fine, or you can go ahead and say, well, that's 0.20. So they should get it right 20% of the time. Part B says, set up the alternative hypothesis to test whether the probability of a correct selection differs from random guessing. So this is part A. Part B says the alternative, they use the word differs. That the true proportion differs from 1 in 5. Does not equal. So that's a not equal symbol. So you can use either the 1/5 or the 0.2, but not equal to 1 in 5. But in a realistic setting, the researchers probably aren't interested in a two-tailed test because they're not going to say, ooh, reject the null. The dog does have ability if the dog does worse than they should do under random guessing. Right? So it is really more of a one-tailed setup, so that's what part C says. We'll now do it, set up the alternative hypothesis where the p-value is greater than random guessing. So greater than 1/5 or 0.20. Okay, now part D gives us results of the study. And we're going to go ahead and conduct the hypothesis test. It says, in one test with 83 stage 1 lung cancer samples, the dogs correctly identified the cancer sample 81 times. What did they just give me? What information?
N.
Okay, they gave me N. N is
P hat. 83.
83.
And they gave P hat.
Did they give me P hat? Indirectly, but directly they gave me X, the number of successes. So X is 81, so then P hat is 81 out of 83. And go ahead, let's go ahead and get that as a decimal. Point what? 9759. So these dogs got it right 97% of the time. That ain't bad. And it's quite a bit better than 20%, which you would expect if they were just guessing. Right? So the eyeball test, right, that Jory likes to do, what would you say? Does this study provide evidence that the dogs can be trained to detect cancer? Yeah, that's pretty clear evidence. You really wouldn't have to even finish it and do a hypothesis test, except if you want the credit on the test. You probably should finish that. So this is step number 2. What's step number 3? Determine the correct step or procedure to use on the calculator, which is the same as it was this whole section, which is what? Use one prop Z test. Okay? Step 4. Compute the test statistic and the p-value from the data. Right? That's the data. This is the hypothesis. So you're going to enter in your calculator, you're going to enter x equal 81, n equal 83, and you're going to select prop greater than 0.2, which I forgot to put up here. P0 is 0.2. Right? Guess what a real common mistake is for P0?
2.
No? Putting P hat in for P0. Well, it's a P, I'm going to stick it in there. Right? But if you put P0, then you've changed the null hypothesis to P equal 0.97. Are you going to find any difference? Right? You said test to see if it's different then. Are you going to find a difference between the data and your null hypothesis if you put the data in your null hypothesis? No, you've made them exactly equal. So you're never going to reject that null hypothesis. So it's 0.2. Now, what was your question?
I was just going to ask you about the P0. You always use that value, the null hypothesis value?
Yes. Yes, this P0 is from the null. And I purposely chose a problem out of this homework set that did not have P0 equal 0.5, because an awful lot of them in this section do. And the one I did in class with the ESP guessing had P equal 0.5. And some people always start to think, well, it's just always 0.5. But it's not. It's whatever fits the scenario. Here it's 0.2. Okay, so go to the calculator. Let me do it up here. Stat, then test. Then the fifth one down is one prop z test. P0 is 0.2. X is 81. And N is 83. They ask us to do this one in part B. They say, now using the hypothesis for part C, which is the greater than one, conduct the test. So use the greater than P0 and hit calculate. And you should get Z equals 70 or 17.67. So the Z test statistic is 17.67. Now before I go any further, is that a big Z or a not so big Z? It's huge. Remember what Z is. It's, what is it? Number of standard errors. When you get to 3 standard errors, you're already way out there in the tail. Remember, 99.7% of all p-hats should be within 3. You're at 17. That's way out there. So the p-value, well, the p-value, remember, is the shaded area out past that Z. So that's nothing. So here's the p-value. It's the p up there that doesn't have the hat on it. So it's 3.669. Now, when you look at that p-value, is that bigger than alpha or less than alpha? Huh?
Isn't it e to the negative 70?
Oh, did I miss something? What does the p in p-value stand for?
Probability.
Probability. If I write this down, 3.669, and go on to the next problem, then I'm not thinking too good. But look around the room, there's probably 5 people in here. About one in 5 make that mistake. They forget to notice the E minus 70 and they just write it down. This can't be a probability. And I get this. This number is greater than 0.05, therefore I fail to reject the null. That's why I want you to do the eyeball test. Look at this number and go, wow, 81 out of 83 times, that's pretty strong evidence. But then they come down and write an answer. I have not sufficient evidence to say that the dogs do any better than guessing. Think about what you're doing, and you should catch those kind of mistakes. It can't be a number that's bigger than 1, so there's an E minus 70. What does that E minus 70 mean? Times 10 to the minus 70. Now, I don't know if you know much about these kind of numbers, but that's a really little number. That means move the decimal 70 places to the left. So I got a decimal, 69 zeros, and a 3. Now, what is the p-value again?
Observation of the data.
It's the probability that
Probability.
if the null is true and the dogs are just guessing, that's the probability that just by random chance they could get 81 out of 83 correct. Or more. In other words, it ain't never going to happen. There's no way in God's green earth that these dogs could get it right 81 out of 83 times if they're just randomly sitting by one of the 5. So, if it can't happen, but it did, remember this is a conditional statement. This is if the null is true. So if it cannot happen if the null is true, but yet it did happen, what's the conclusion? The null can't be right. Reject it. So this is essentially the probability that the null is true. It's not true.
Does it matter if we write 3.669 e negative 70?
No, that's fine. Yeah, you could write E minus 70, just like your calculator shows, and I would accept that. Don't just write the 3669, though. I will go nuts on that one. Okay? Now, oh darn, I'm out of time. What I wanted to do next is compute a confidence interval for this. Because there is a one-to-one correspondence between hypothesis test and confidence intervals. So I'll have to do that next time. But you can use a confidence interval to do a hypothesis test. And I recommend that you always do, just to make sure that, am I making the right conclusion? Am I doing this right? Because confidence intervals to me are easier to understand than p-values. And they give you the same information. All right, we'll see you next time.